Okay, let's get started again. This is again really process design rather than necessarily pilot plans, although pilot plans is a major item in here. What we're doing is determining whether the equipment has been properly sized or not. And in particular, we're very much interested in finding out what does the work as opposed to the size of the job. Just as a quick review of some of the things we talked about earlier, we have the small scale, which is right in here, and we have the large scales here. Now, typically a chemical reaction, I brought this up last time, chemical reactions, this will work fine. Subtle bit of solids. There's enough solids available to run the reaction. However, on scale-up, these solid surfaces are not available for processing since they're sitting on the tank bottom. They were available over here in the fact that there wasn't a lot of concentration, surface concentration needed. So the small scale of the reaction worked well, or worked, and in the large scale the reaction essentially disappeared because the solids were on the tank bottom. Essentially, you need to raise the solids off the tank bottom and have them fully exposed to processing, and then you have a working system. Here we have a grinding operation. Small scale was it was fine. Grinding times was an hour. And when we go to large scale, what we find is that we need to add, well, first off, you should identify the physics. You have a particle that's approaching the blade here. You have high-speed movies of this, perhaps, and just as the particle touches the blade, it disappears. So by that movie, you can figure out that the working area is right in here, and we have to add more blade area, grinding surface area, so to speak, to make this a effective processor, similar to the small scale. Okay? Anyway. Moving right along, I think we ended up talking a little bit about flotation. Small scale, everything worked fine. Large scale, you had a huge dead area in here. Again, they're geometrically similar. But we have a large dead area in here that was not being harvested. So we come along and put in troughs along the top grid here. And we're able to harvest this area in flotation. Moving right along again, you could test this by perhaps spreading dye on this surface and seeing if it flows over into the weir. Good design is where most of the dye overflows into the weir. So if this does not occur, improvements can be made. Okay. Fast precipitation reactions, the idea is that what happens is, I'm going to go up here to the slideshow from this slide. You have a feed plume coming in, right? And going for color again. So you have a feed plume that's here, and that will be an L squared, the area involved there, that expanding feed plume. You have basically the reactor is right here. The reaction is occurring around the perimeter. So what happens is you have a 2 pi r effect, 2 pi r L. So I have L over L squared, and I have a 1 over L situation occurring. At large, well, first off, this points out that the size of this feed plume will determine behavior of the process. So you will, in fast precipitation reactions, you will have a scale effect. Anyway, moving right along here, and let's try going back. We'll end the show and discard. So this is a very famous accident, or excuse me, this is a very famous scale-up, a large chemical company. We won't say who. Small scale, they had a boiling reactor. Large scale, they had something looking like this. So this is 30 feet here. So the top portion of the reactor was boiling, and the bottom portions of the reactor, due to the hydrostatic head, was not boiling. There's a much higher pressure down here. As a result, boiling is a surface phenomena, correct? And it was required to have boiling, it was required for the production to have boiling to occur. As a result, a substantial drop in production here due to the fact that only 1/3 of the reactor was being utilized. The scale-up should not have been geometrically similar, but instead, let's go into this again. It should have been a scale-up that, I guess I don't have my pointer. I guess I got to go to my pointer. Highlighter. The scale-up should have been like this, a flat tank where you have an impeller here, and here you have another impeller, and here you have another impeller, and the liquid level would be about like this. So it would be a large horizontal tank for the boiling. The company had these types of tanks, so they immediately scaled up into a bad geometry, resulting in loss of production. So you never think of boiling as being non-scalable, but it is. Reactor is filled, lab reactor is filled with a boiling mixture. You have a non-boiling higher pressure volumes that are non-productive, right? So boiling is a non-scalable process. Lots of processes are not scalable. When I was a young engineer back in the 1970s, there was a rumor that a huge pharmaceutical company or a pharmaceutical company in Indiana had problems in scaling up one of their fermentation processes. Here is probably what happened, although I don't know for sure. The small-scale fermenter worked fine. By the way, I will have to say that small-scale fermenters should be using the Smith impeller or the hollow blade impeller. Anyway, small scale, they had the behavior where the gas went throughout the entire reactor or fermenter very well, and they thought that on the large scale you would have this happening. Unfortunately, you have around the impeller a gas band formed, and the rest of the reactor or fermenter was a bubble column. Around here, there would be 50% gas. Here, down at the bottom, there would be 0% gas, and up here, bubble columns are typically 15% gas. So the reactor was essentially the 50% gas. What you can do is perhaps stack these. So you have an impeller here and an impeller here. If you stack these, sparge to each impeller, you may have the equivalent of 3 reactors. Unfortunately, that didn't happen. Laboratory reactors filled with gas, actual plant operations are often substantially less than laboratory projections. Here you have lab experiments that were done. This over here is the KLA. That's sort of a performance index. And this is the worker or power per volume type of item that people often use. Correlate mass transfer. And the lab data was down in here. So they projected, this is down around 300 or 400 units. They projected on up, straight on up, and projected a production of around 10 or 12. Whereas the actual production was about 2. And what has happened is you have a flow regime change. What occurred small scale here did not occur large scale. You have a flow regime change where you have a gas band around the impeller and a bubble column of the rest of the tank. As a result, you had a substantial reduction in performance. And in this case, you were expecting 12 and you got 2. 16% of what you thought you were going to get. Upper management was definitely did not like that situation. Missed opportunities, trap reversals, okay? You have LN plus 1 traps occurring everywhere. These can be done also in the reverse direction. On a small scale, there's some sort of surface behavior that has a negative influence on the process. So the scale-up was stopped because of poor lab results. However, on scale up, these negative surface behavior, or the negative surface behavior, would be far less important. But people don't realize this. As a result, on scale up, such behavior would not even occur, and they stop to scale up. Do ln plus 1 processes really fail? The answer is no, in lots of cases. They sort of limp along. They have just poor performance. People accept the poor performance. The efficiency is low. If there was complete failure, which is really a great idea to have complete failure, then the failure could have been dealt with appropriately, but it's not. It is not dealt with. Maybe not even recognized. Poor performance is accepted. Processes limp along, as I said. Attempts are made to correct the problem using operating conditions. That's a typical occurrence in industry. You turn the rotational speed up, or actually, operating conditions can be changed to compensate for poor geometry. It's far better to have the good geometry to begin with. Okay. And we have several options here that we'll talk about. Overcoming the traps. One is to change the geometry. Back here, we said we'd add an impeller here, sparse it, add another impeller here, sparse that. That would be a wonderful solution. But you have changed the geometry, right? So, anyway, let's see where we are at. So, let's change geometry and see what happens. It's desired to cook at the same rate, small scale as large scale. We have two processing differing by a factor of 1,000 in volume. So, cooking rate, same cooking rate, large scale as small scale. What's that actually mean? It probably, you can interpret it in mathematics as the heating rate scale 1 to the volume scale 1 equals the heating rate scale 2, volume of scale 2. That would be the way you would state the scale-up objectives. You've got something in words, and now you have an equation which you can work with. State the process objectives, what are important, what's the process similarity you seek, what are you trying to do? Okay. So, moving right along, we see the volume varies with impeller diameter cubed. We're looking to see what is doing the work in the process, what's the controlling mechanism, what's the size of the job, some standard questions here. And we look, and so Q has to come through a heat transfer coefficient, which we talked about earlier, some sort of area, and some sort of driving force, delta T, heat temperature difference. And we plug in. Now, we're going to go with geometrically similar processes, which means that area for heat transfer is going to be d squared. You're going to heat through a jacket, or you're going to heat through coils. But these would all amount to items that require this. In a sense, this is not the way you want to do the scale up. Anyway, let's see what happens when we assume area is d squared. We plug in volume's d cubed, area is d squared. We're going to claim that the driving force for heat transfer, this delta T, is the same. Okay? Or the end result of the equation is heat transfer coefficient divided by diameter 1 equals the heat transfer coefficient diameter 2. What are the process physics and the chemistries? What's those flow regimes? Process physics is heat transfer. Chemistry is not important. Flow regime is turbulent. Geometrically similar systems are going to be fixed. Geometrically similar serves as a similarity, serves as a starting point for the reaction. When we do that, we go to the heat transfer correlations, which we've seen before, and remove all leading constants, geometric ratios, and fluid properties. Or we have that the rotational speed scale 2 is 10 times the rotational speed scale 1. That's not possible. Scale up. Now we got to check for a judgment to see if it's possible. The results are reasonable. No, they're not reasonable. 10 times the speed in the lab. It's unreasonable. Can the process be accomplished? No. Will it be a working design? No. 10 times the rotational speed is not available. See, scale up has to be practical. So we stop. There's nothing wrong with the desired process objective since it's a realistic objective. Lots of processes cook at the same rate on scale up. The problem is geometric similarity. If geometric similarity is not followed, then the process becomes reasonable. We have area now. Then let's take area and change it to diameter cubed. So we have heat transfer coefficient equals heat transfer coefficient. And that's possible. This is the same as the example of equal heat transfer occurring in the burning problem earlier. So equal heat transfer rates become possible by changing the geometry. I recommend direct steam injection, basically direct heat addition. Or if you're cooling, direct cooling with, say, liquid CO2 or something, liquid nitrogen. Heating coils, not really. Pump around loops, not really. Van-Allen heat exchangers probably would be helpful. Van-Allen heat exchangers are phase change heat exchangers typically, where you're changing latent heat. Engineering point, you break with geometric similarity. Many processes become possible. Process similarity becomes possible if geometric similarity is broken. So a lot of people think geometric similarity is required for scale up. It is not. Geometry is a major design variable and should be used effectively. Now quickly, let's go and see if I can give you an example of where there was a scale up where you added large quantities of heat transfer area. Let me see down here. Static mixers is an example. Now, in large exothermic reactors, you have the addition of heat, right? Bubbles. This is the one. Here's an example. Basically, you have, say, a boiling reactor system here, and you got to get the heat out plus get the heat out. So you find out the entire reactor is filled up with heat transfer surfaces. And this is an example where heat transfer would be diameter cubed. The heat transfer area would be proportional to the diameter. Again, static mixers. Again, the entire reactor is filled with heat transfer surfaces. Nuclear waste storage tanks are filled with heat transfer surfaces to get the heat out. You need to get the heat out. You can get the heat out by shown here with heat transfer surfaces, or you can get the heat out by boiling. If you don't get the heat out, then you have a possibility of industrial accidents. So let's go back here. Let's go back down here. Okay. An example, that was an example of right in here, area varies as diameter cubed. Of course, you got a serious cleaning issue with all that heat transfer surfaces. So the option one was to change the process geometry you're using. You went from something that was geometrically similar, you broke with geometry, you broke the similarity, and now you can successfully do the scale up. Option two would be change the process objectives. Okay, that's very important. Let's try another example. This leads to an impossible or very difficult scale up, and we manipulate it into a working design. Suppose on scale up, which is often the case, you want to mix the same small scale as large scale. Now then, if we go in and study mixing, we understand that what you should be dealing with is not mixing time, but mixing revolutions. Essentially, if you have geometrically similar systems, you have n theta 1, this is number of revolutions to mix, is equal to the number of revolutions to mix on scale 2 if you have geometrically similar systems. This is backed up by correlations. N theta is a function of geometry, primarily a function of geometry. If you keep the geometry constant, then N theta is constant. So for equal mix times, theta 1, mixing time theta 1 equals mixing time theta 2. And then you have N1 equal N2 very quickly. So for scale up, rotational speed scale 1 equals rotational speed scale 2. Okay. However, the unfortunate situation arises if I take a look at the power calculations, the difficulty arises. For turbulent flow, we have power is proportional n cubed d to the fifth. Now then, if we keep if we keep rotational speed constant, we have power varying with diameter to the fifth power. Between power scale 1 to power scale 2, n being equal between the two scales, scale 1 and scale 2, we have power varying with d to the fifth. So, if we are going from scale 1 to scale 2, trying to maintain n theta mixing time the same, right, with rotational speed, equal mix times on scale up are unrealistic. Large scale tanks will take a long time to mix. So the process objective is basically impossible. Right? One possible way to help in the processing to determine the mixing times that will be needed on the large scale. So instead of scaling up equal mix times, we now scale up. The large scale process will be 10 times the mixing time of the small scale process. Okay, that's just what you pick. And now you drop down here, and that means n theta 2 is 1/10 n theta 1. In other words, small scale is at 300 RPM, large scale would be at 300 RPM, this would be at 30 RPM. In terms of power, you can run it, because small scale perhaps it runs at 3 horsepower, and at scale 2 it will run at 300 horsepower. Right? So the idea here is you change process objectives. You can't do some things due to the practical limitations of equipment. So you modify your desires by choosing another process objective. Here we changed it. The large scale will mix 10 times more slowly than the large scale process will mix 10 times more slowly than the small scale process. Reynolds number, well, there it is, 10 times the Reynolds number. So it is well known that large tanks are far less turbulent than smaller tanks for the same Reynolds number. It's very important to realize that. So the idea here is on scale up, you have to accept what is practical. That means you may have to change your process objectives, and you may have to change your geometry. Both are very important. Now let's move on. We're going to talk about objectives and scale changes. Objectives. Now I've just rattled off some objectives. You're always starting with objectives or needs that generate objectives. So let's see what we have here. Some process objectives have different levels of difficulty, different levels of complexity. They range from the most general to very specific statements. They can be very vague and undefined to highly detailed. Process objectives are easy to accomplish, and some are not so easy to accomplish. So let's take a few here. Key point in design is to obtain appropriate process objectives. This is a central point that people often miss. Process objectives determine the type of process you're going to have. Process objectives determine the equipment. Example, this is coming from a very good friend of mine. Worked inside DuPont for many, many years, Dick Goodley, very good friend of mine. He was talking to me about this example. You're asked to make a colored polymer, okay? You're asked to make red plastic for kids' fire engines. You have a toy fire engine, and it's supposed to be red. So you're asked to make red plastic. And you go ahead, and that's fairly easy to do, actually. All you do is add red dye and mix it in. And it's no more difficult than anything else. So the red fire engines were made, and over the summertime, these red fire engines turned pink. By fall, everybody was disappointed that their red fire engines were no longer red. So the people up top says we now have to make red plastic or red fire engines with color durability. Okay, color durability. And basically that would require a pigment to be added to plastic. Now dye is fairly simple. Dye is being a liquid dye. There's no air in the liquid. Here, pigment is a powder. Powder naturally contains air. And so to mix in pigment into plastic is a higher level of difficulty than simply red dye. Basically, it's a dispersion of pigment into the polymer is a difficult task. So a big difference in process objectives. One is red color. Another one is red color with color durability. You went from an easy process to a very difficult process, and to get your color durability. If you notice that I recently had a plastic part break in one of my appliances at home, and you can see there's a big, large air bubble in that chunk of plastic. Okay. Anyway, just as an example of the problems in facing some processes where it doesn't occur in other processes. So, if you do have process failure, you may need another type of equipment, another processing strategy entirely, or a need to change the process objectives. This is actually a very important statement. You will have troublesome areas, fast processes which require uniformity with large throughputs. See, uniformity and large throughputs, those don't go together well, right? Uniform size and large throughputs. Large throughputs usually mean turbulence. Turbulence usually means non-uniformity. Uniformity usually means laminar flow, and laminar flow is not large throughputs. So these are actually contradictory objectives here. Particle attrition, very interesting subject. Whenever you have particles, you're going to have them abrade each other. Anything nonlinear, pH measurements are notorious in mixing. Coloring or dyeing fabric is a problem. Any processes that are exponential will cause you problems. There are, of course, processing tricks available, and a change in their processing approach may be necessary. It's important to recognize problems in the development stage. It's far less efficient to identify scale-up problems in the plant. One needs to enhance problem recognition skills, and the first basic step in design is establishing a good mixing design. Okay. Scale and process type. Processes change with scale. Substantial changes of volume and surface area occur with scale changes. Processes are often surface area processes, volume processes, or surface to volume processes. Let's just take a look at this. All this up here and all this down here, we'll get to in a second. Scale, 1, 10, 1,000, 1, 10, 100, and 1,000. In terms of length, it's 0.01 meters, 0.1 meter, 1 meter, 10 meters. If I take a look at surface area, I'm just taking the surface area of the inside of the tank, right? You quickly find that the area, this goes up by a factor of 10. Area goes up by a factor of 10 squared, right? This is 10 squared. Volume goes up by 10 to the cube. So if I look at area per volume versus scale, I see that area per volume goes down with an increase in size. Area is becoming less and less and less important. Volume, on the other hand, becomes much more important. This is a factor of 10 here in volume reduction. This is a factor of 10 here in volume increase. And people don't really recognize how much volume there is on the large scale. Scale of 1 to 10, you have a volume increase of 1,000. Scale of 10 in length is 1,000 in volume. Scale up of 100 is 1,000,000 increase in volume. And although it's not apparent, you have substantial increases of volume that are simply not recognized. Okay. Going over here. Wall surface area per volume, or any area effect, is much greater on the small scale. So you have wall edge effects, end effects are much greater on the small scale. Area-dependent processes need additional area on scale up. Tank walls, often catalyze reactions or participate in the chemical reactions on the small scale. These will have a much less effect on the large scale. The reason why you use glass-lined reactors is to prevent the wall from participating into the process reaction kinetics. Wall effects and end effects on scale up and their effects, and the lack of their effects on large scale, causes process differences with scale. Very famous person, Jim Olshu. I have taken this slide from his work. It was a very simple slide that actually has profound implications for scale. If I go small scale to large scale, I have increasing volume effects. If I go the other direction, large scale to small scale, I have increasing surface effects. Exothermic reactions with large heat releases cannot be accomplished on the large scale. If they are, they might wind up being explosions. The heat cannot be generated fast enough, so there may be a change to a boiling process to get the heat out. Example of the heat evolution. On YouTube, I saw this scale up of this reactor, and it was an exothermic reaction, and basically the heat the heat release on the large-scale calculations was so great that the reactor equivalently vaporized. T2 accident. You go on YouTube and look up the T2 laboratory accident, and you can see a very large exothermic reaction that they could not get the heat out fast enough. Scaled down studies may not be accurately represented by volume effects. It may not be possible to accurately scale down processes, right? So, volume-dependent processes are much more difficult to represent on the small scale and to the large scale sizes. Scale down studies may not be accurately represented. Slower reaction. This is kind of cool. Slower reactions appear in chemical reactors as they become larger. Larger usually means that the processing times are longer. That means whatever reactions there were, the slower reactions will eventually appear that were not observed at all on the small scale. And when you age wine, I'm not exactly a big wine connoisseur, but I enjoy wine. And supposedly, as you age wine, it only gets better. And this morning when you got up, or whenever, you went into the kitchen or your bathroom and turned on the water. And the water came out of the faucet, and you turned on the water, and you turned off the water. No problem whatsoever. But if I take a very large pipeline, right, let's go into very large pipeline. So I have this real tiny little pipe up here. And turning that on and off is not much of a problem. It can be handled with no difficulty. However, if the pipeline is huge and the material in that pipeline is going at 10 feet a second, say, and it's 15 miles long, okay, the length is 15 miles long, okay, and that's not 15 meters, it's 15 miles, and it's 2 feet in diameter, right, then you have substantial momentum. You turned off this pipe flow in a matter of 5 seconds, maybe at most. This one will shut down this pipeline and close it off. You will spend maybe an entire morning. You get up, you may have your crew there. They get up and turn the valve 1/4 turn, maybe not even that, and then they'll sit down. 15 minutes later, they'll get up, turn it another 1/4 turn, and then they'll sit down. Get up, turn it another 1/4 turn, and sit down. They do this every 15 minutes or so, and eventually they'll get the pipeline shut down. Anyway, you haven't heard what the problem is yet. How can you recommend building a database to solve it? We always build a database. Well, we'll need coffee mugs for the team project. The problem is we have poor processes. Oh, that is so true, right? We have poor processes. And that could be the slogan on our coffee mugs. I don't care what process you have, you can always do process improvements. And it's amazing where they may lead. Small retrofits can actually lead to very large improvements in profits. The problem is that you have a lot of resistance to change. And I don't blame these plant people. I mean, they don't want to go down a road that's difficult to recover from. The other thing is there's so many people out there claiming that they have the secrets, the magic secrets to everything, that you eventually get tired of it and you don't want to do it. You want to just maintain status quo. So I don't know, do you go for changes or do you go for maintaining the status quo? Actually, I'd probably want to do both. Simultaneously, you don't let them touch your plant equipment. However, you explore the possibility of doing substantial process improvements. Shall we move on now to see what we got here? Basic concepts in applied mixing. Okay. What I'm about to say about mixing applies to most operations that are not predictable. Plant is a string of unit operations, is a line of operations. A working plant is the end objective. There is an enormous number of mixing-dependent processes out there, and mixing may control the success. See, getting back to the beginnings of chemical engineering, there were 4 areas of chemical engineering. One was fluid mechanics, one was heat transfer, one was mass transfer, and the 4th area, this was back in the 1920s and 30s, the 40s, maybe even the 50s, the 4th area of chemical engineering was contacting. And for some reason, that area has dropped off and disappeared, or collapsed down into this area of mixing, so to speak. Anyway, let's go on. If mixing and contacting is wrong, then everything else is going to be wrong. You're going to have yield losses. You're going to have separation process problems. You're going to have processing bottlenecks. You're going to have production limitations. When you improve mixing, benefits can occur, such as increased production rates, better quality product. Mixing information, proper mixing is economically significant. This is an example of a very large chemical company. They built a plant. I tell you the name, but I get in trouble. Maybe I get in trouble. Anyway, built a very large plant. Cost them $25 million. They couldn't start up the plant because the solids could not be suspended off the tank bottom. This is a very large reactor. They needed solids off the tank bottom. The solids probably fused together or agglomerated on the tank bottom, and they couldn't start up the plant. Processes can limp along with unidentified mixing problems. This is an example of poor scale-up. Poor operations are a result of poor scale-up. 5% yield loss in high-valued material can mean $5 million a year in profits. Again, I'd mentioned who these are, but I best not to. Simple mixing test is 6 weeks carried out in the polymerization reaction. Cost of the test was $250,000. Benefit was $5 million a year. Simple retrofit, which was basically adding a baffle in the right location, resulted in $160,000 a year savings. A new design may be $0.5 million a year. So mixing problems cost anywhere from, say, $500,000 to $5 million to solve. Usually they're a lot cheaper than $500,000 to solve. $5 million is probably too excessive. Costs are hidden because mixing problems are not identified. This is very, very true. People simply tolerate the situation. Internal survey of a major chemical company. They reported a potential dollar loss of improper mixing ranging from $0.5 million to $10 million per year. And improved mixing, or potential benefits, you'll have yield improvements, better quality products, decreased cycle times, i.e. you eliminate lump production would be great addition to processing. And, of course, you can have capacity improvements. So, typically, if you also have new processes, new incentives are similar of magnitude. Objectives are minimize development costs, shorten commercialization times, increase yield and purity, and improve uniformity. This is coming from a good friend of mine. I won't mention his name, but I will acknowledge that there is a chap who gave me this. Low-cost retrofitting is key to rapid commercialization of chemical discoveries. Low-cost retrofitting, right, is key to rapid commercialization. This guy ought to know. He was in the business. So if we take a look, chemical process industry, year 2000, was about $900 billion a year. Improper mixing costing us anywhere from 0.5% to 1.5%, or $4 billion to $14 billion a year. You realize how many, quote, mixing experts there are in America? You can probably count them on your two hands. Current investments in mixing is about $150 million a year. The cost of mixing equipment is low, very low. Cost of ineffective mixing can be actually very high. So it's very important to recognize this. Proper resolution of mixing contact problems is continuing education. The problem is not even identified. You need to develop the proper perspective on the process, and you need to apply fundamentals. Economic costs and losses because of inadequate mixing and contacting. You could perhaps lose your initial capital investment, losses in production, losses in quality, downstream separation costs, increased safety and environmental costs. Range of problems. Range of problems encountered is huge. Various sources of variations include multi-phase and volume fractions, variations in that, rheology of the phases, processing geometries, including the internals. Processing energy levels, different flow regimes, boundary and initial conditions. Certainly there's no chance for a single geometry to solve all these problems. Right, let's go back one here. There is no universal pilot plant facility or ultimate practice, or ultimate best practice. There will always be something better. There will always be something better. Okay. Everything becomes a special case. You should have different methods and different equipment for different processes. The engineering situation. Well, mixing is poorly understood. It's highly empirical. Fundamentals are limited to as applied to the process. Models are rudimentary. Unpredictable unit operations exist. Data needed for design and modeling are not available. Many different process objectives, many designs. There are a hierarchy set of process objectives. It should be clearly stated. It should not be implied or hidden. Again, I said this earlier. Your objectives form your wish list and become your performance indices. And processes are not going to accomplish all your objectives. Right. Fermentation process can have a multiple number of objectives, right? You can have nutrient supply, which would be a blending operation. You have oxygen supply, which is a gas dispersion operation. You want to maintain living cells. Those are some of the objectives in fermentation. Actually, you should look at these and see which one is the most difficult. And the second one here, oxygen supply, is perhaps the most difficult. In other words, if you have a good gas dispersion operation, you will get a good blending operation, and you will maintain low shear, which helps the cells to continue to live. The bottom line in design is you want to get the right equipment and the right method for the job. And so often this is not done. Right. Correct design and over-design. Well, over-design is thought to be the quick fix. It's only a minor cost. Well, over-design can actually be detrimental to the process, may lead to quality problems and increased production problems. Problem areas, well, for process mixing and contacting. If you notice what was the variations that I cited earlier, there's an overlap between the variations and what you're trying to do and problem areas. Multi-phase systems and viscous systems, systems with complex internals, systems that have too low of an energy or too high of an energy. You don't want to burn the material. Some processes can put in enough energy where the material actually burns or shear degrades with high temperatures. You don't want to mix in that. Systems with short time scales, right? Systems with poor initial distribution and systems with large volumes. Scale matching, we've already talked about that with the powder and falling liquid curtain. However, let's take that, add some more here. Foaming occurs everywhere in industry. Foaming can be broken up with spray. If you look, the spray length scale and number are similar to the foam bubbles. The size of the droplets is the size of the foam bubbles. The number of droplets is the number of foam bubbles. So we're matching size and number. If I'm dispersing powders, I wet the powders out using wire whips. Here, I want the powder particles are small. The wire whips are also small, and I have a sort of a match there. For cause and effect to occur, length scales have to be similar in size. This is very true. Avoid mismatches. A mismatch usually means over-design mistakes and waste. Scale mismatches may be a sign of poor design. For example, a fast chemical reaction occurring in a slow mixing device. Okay, with a slow mixing device, the reaction is controlled by it. The reaction is controlled by the mixing. So you have a mixing control reaction. You can't have a reaction without mixing. You can't have a reaction without getting the materials together. Time matching of scale and equipment at the time of the reaction, right? Some reactions you mix and mix and mix and mix and mix, and then 3 days later it reacts. So mixing is not very important. However, other processes, the reaction takes place as you mix. So the reaction takes place as you mix. So whenever you deal with chemical reactions, not only do you have to worry about the flow regimes and how they are mixing, but the speed of the reaction to the speed of the mixing. Multi-phase systems, well, more questions have to be answered. That's all there is to it. Information needed for multi-phase is expanded greatly over single phase. However, significant similarity exists. Now, this is kind of a little key item here. Similarity helps in understanding the design. Gas dispersion is mass transfer limited. Solid dissolution is mass transfer limited. These are very similar to each other. Both processes depend upon power per volume, and both processes will behave similarly, believe it or not. Significant similarity exists between different multi-phase processes in the same equipment. The multi-phase processing in a particular geometry provides information concerning other multi-phase processes. Right? So this information can be used as an analogy, so to speak. If it happens this way here, it will happen the same way there, basically. Processes may be very similar if they have similar objectives. So this gives rise to what might be referred to as process-specific mixing designs. More process-specific mixing designs have emerged, more effective at accomplishing the objectives than the standard multi-phase purpose designs. Improved process performance is likely. Standard multi-phase purpose designs never worked well in the past, by the way. Some multi-purpose designs, we have the Smith impeller or the hollow blade impeller for gas dispersion. We have hydrofoil or fluid foil impellers for blending operations. And we can have a double helical ribbon for viscous mixing. Everything can have a significant effect upon the process. Few things do. The trick is to identify the controlling quantities of your process. The other thing about mixing is you got to recognize you have all kinds of different types of mixing out there, and you should be aware of them. First mixing can occur by natural convection. Well, first mixing occurs by mechanical agitators and by jet mixing. Now, of course, you must realize that there's natural convection mixing, shaking, tumbling mixing, boiling, and bubbling mixing. A pot on the stove that's boiling water, it's well mixed. If I take a shaker, that's well mixed, and shake it up. James Bond said, shaken but not stirred. Shaking is essentially similar to stirring, right? Shaken but not stirred. It's sort of like the distinction between an apple and an apple. Naturally, don't ruin James Bond's favorite statement, right? But anyway, natural convection has saved lots of people's lives, right? Lots of people's lives. So what we have is a mechanical mixing. The impeller and tank determine the geometry. Geometry's key. Do not use turbulent mixers in a laminar application. This is coming to me from another good friend of mine, Don Kessler. He used to work for a very famous specialty chemical company. Don Kessler is the one who gave me that. And it's very, well, I shouldn't say he gave it to me, he emphasized it over and over and over again. So you have mixing by these other mechanisms. You have now to recognize that there are mechanical mixing geometries, and here we go. Some laminar mixing geometries. Actually, on this page is mixing geometries. I wouldn't use any of them, okay? They're here, just as a teaching aid, so to speak. Let's take this one, for example, right up here, and we will, how can we do it here? Slideshow from the slide, okay. Pointer, highlight. Now then, first off, you do not want these support bars in here. That's ridiculous, okay? What you do is support this on an anchor. So you have the anchor down here coming around and up. So if I was to redraw that, let's try color and let's try blue again. I would have the anchor come down here and support the helix, right? And I would get rid of these crossbars. The reason why you would want to get rid of the crossbars is so that you can come in from the head and make process measurements all you want to, right, without being affected by the rotation of the impeller. Okay, let's go over that again, look at it one more time. The other thing I should recognize is the flow pattern. Either I pump up at the wall, whoops, guess I need my pointer. Pointer option, color, let's try orange. I want to pump up, I got my yellow again. I want to pump up at the wall, so I'm pumping up at the wall. I'm using my anchor to be a wall scraper. And then I want to pump down in the center of this thing, center of this. So this is a double helical ribbon with bottom scraper. It's a double helix because you have two of them. Excellent. A single one doesn't do the job. So you really need double helix. Mounted on an anchor, and typically you do need wall wipes to improve the heat transfer. So there you go. Excellent mixer. This might be considered a universal mixer. The only problem I ever had with it is I think we were pumping down. It causes solid impaction, and we bent the shaft, or we bent the ribbon. We were astonished. I mean, this steel, there was a lot of steel in that impeller. But this would be a three-dimensional mixer. Lots of good advantages to it. Over here has also been studied in literature. It's an excellent mixer as well. Obviously, it's a helical screw. Okay, this is a helical ribbon. Okay, excellent, excellent mixer. But it's in a draft tube, and between the two, I would want to pick the helix by far. Down here we have the typical design that you find in undergraduate textbooks on mixing. First off, this is a fairly ridiculous design in that if the liquid level falls below the agitator, you lose mixing. So if you're filling a batch of bottles, if you're filling bottles from a batch, as soon as the agitator reaches the bottom of the tank, as soon as the liquid level reaches the agitator, you have lots of problems that can happen. You can have foaming, splashing, bubbles, not bubbles, but foam. When it drops below the agitator, then this whole area is essentially no longer being mixed. So one always wants to have an impeller on the tank bottom. So if I take a look at that, changing my colors again, what I really want to do is extend the shaft of that impeller all the way to the tank bottom. And I always have a small impeller on the tank bottom to maintain solid suspension. Right. I also perhaps would want to run a cone bottom which may or may not be baffled. I suspect you really need to be baffled. And then I would run a tickler impeller all the way down into the cone. This way I could add different volumes in here. But I'm always looking for the fact that the liquid level can drop below the agitator and I lose mixing. Wow. I don't particularly care for radial flow impellers because what happens is they compartmentalize right down through the middle. This up here may be quite well mixed. This down here may be quite well mixed. But cross mixing between those two volumes may be somewhat limited. If I go to this tank, obviously again, as it now sits, there's a dead zone here. Okay. The way you get rid of a dead zone is you put a feed through it. Good idea. But again, I don't have agitation when the liquid level drops below the agitator, so I always want to bring it down and have a small agitator on the tank bottom, and that actually sits in the dead zone. Further on down, I may have a cone bottom down here, and I need a tickler impeller to go all the way down into the bottom of that tank, and away I go. So those are some comments. Excellent mixer, impeller on the tank bottom, radial flow, not a good idea. Here the flow will be the full tank, and I will be able to mix, no stratification occurring. So between the two, these two are perhaps this on an anchor. We've got to have our anchor rather than the support arms. I already said this. Okay, often causes quality problems. Always have an impeller on the tank bottom. Jets mixed by air entrainment. Now what happens is, first off, you got to recognize when do you use jet mixing. Well, jet mixing occurs everywhere. You go home and fill up a glass of water from your sink. That glass of water is well mixed. You turn on the water, you will naturally well mix that glass of water. So you always have jet mixing, and we'll talk about jet mixing a little bit later. However, jet mixing is particularly useful for very large storage tanks. So you have a very large storage tank, maybe this is 40 feet in diameter, whatever, and you do not want to have the jet along the tank bottom. What you want to do is have the jet fully expanded and exposes the surface area to the mixing. So this is the type of thing, it may be 2 or 3 days before you get that tank mixed up. Of course, the bottom is, again, a particular area. Even though you had a good mixing jet, this bottom down here may be a collection of debris. The jet mixes by entrainment, so entrainment comes in from the side of the jet. The total momentum of the jet remains in this direction. It remains constant. Some of the stuff slows up as it speeds up the material coming in from the sides. The N theta principle, don't mix out. Very important concept that's completely ignored or often ignored. It's also applicable to lots of different types of equipment. And basically it says your processing is going to be accomplished in a certain number of revolutions. Now I want you to do a simple experiment for me. I want you to go home Saturday morning and I want you to make pancake batter. So your pancake batter, let's take a look at what's in there. You throw in a couple eggs. So right now you have 2 phases. You got the egg yolk and you got the egg white. The egg white is non-Newtonian viscoelastic, right? And it has a structure to it, so it's not exactly a simple fluid. The yolk may be complex as well, but it's certainly a more simpler fluid than the egg white. Then you go ahead and add your oil. So that's the 3rd phase. 4th phase is perhaps you add milk. Okay. 5th phase is you add the flour or the powder. But not only do you add powder, but you're also adding air when you add the powder. Right? So you might want to watch and to see if you get the air out as you mix. Now I want you to count the revolutions. As you're mixing, take a spatula or a wire whip and count the revolutions. 1, 2, 3, 4, 5, 6. And you'll find that it may be 30, 40 revolutions to mix up pancake batter. Now, if you add more powder, or say you add milk and try to mix that in, that may be 30 revolutions to mix in additional stuff. But it's over with after 30 revolutions. Now, you can do that very fast at high speed or very slow at low speed, but it will mix. So you got to stop and think about mixing time, right? This n theta is the mixing time is not important. It's the n theta that's important, right? It's the n theta that's important. This is also true for a lot of rotating equipment. This is something you can take home and bank on. Lots of equipment, extruders, tumblers, mixers, rotary dryers, the processing is done in a certain number of revolutions. Now, we often state this in terms of mixing time. Mixing time is not a good thing to be dealing with. Mixing time can be quite misleading. Anyway, let's go on. So we go and look at the brownie mixes. This is another assignment. And you see here it says beat 50 strokes by hand. That's 50 revolutions by hand. Right? So this is good. Excellent, excellent, excellent. Or we go around and we see beat 2 minutes or 3 minutes at high speed. You got your cake mix, you got your oil, you got your water, you got the egg whites. Okay. And you quickly find out that it says beat for 2 minutes at high speed or by hand for 2 minutes. What that really means is you have a high-speed hand. Anyway, this is fairly bad because the time is can be quite meaningless, right? Time can be quite meaningless. Here's some original data back from Nagata's time. Nagata was a Japanese professor in 1956, post-Japan, post-World War II Japan. Nagata was doing much better research than anybody in the United States was doing at the time. And you can quickly see that n theta, this is rotational speed down here, right? Surprised rotational speed isn't listed there. But the product of these two, right, 80 times 160, I go over here, this is 100, n theta equals a constant. Some of the original data. This is some interesting data. 1985, much better. Different physical properties. And this is with a helical ribbon, right? What they found was they had several different types of mixing patterns. They had a second mixing pattern at the bottom, where n theta was 44. And they have another mixing correlation going up like this. This study is very interesting in that they varied volume fraction. They went from 0.3 all the way up to 3, right? They also, as a result, varied viscosities. Viscosities of a factor of 200, down here 300. Different viscosities and different volume fractions. And if you take a look, forget about all the crudeness and just draw a line across there. I can mix anything with 3,000 revolutions. 3,000 revolutions. If you really want to get into details, then I go down in here. And it's not 1,000 revolutions anymore. It's 100 revolutions or 44 revolutions. So you're running at 1,000 revolutions, you improve your geometry. Now you're at 100 revolutions, and you improve your geometry again, you have 40 revolutions to mix. However, the rule of thumb, if you're looking for a rule of thumb, is anything under 1,000 revolutions you can mix. Okay? However, that's not true. What do you mean? I just got done saying it's 1,000 revolutions. You're mixed. Yes, but that's not true. And it's not true because there's actually two types of geometry. There's effective geometry, right? Effective geometry. And there's non or ineffective geometry. This works because it is this works because this is an effective geometry. It's a helical ribbon. It's an effective mixing geometry. If I had an ineffective mixer, then it could be 1,000,000 revolutions to mix or 10 million revolutions to mix. So the whole idea is you really need to not overmix. It's a waste of time. The problem with time is that it can be quite meaningless. There's an optimum as well. Again, I guess this is n theta value versus wall clearance for helical ribbon impeller. You can see that you have a minimum where you may have 60 revolutions to mix or maybe 130 revolutions to mix. But up here it's 150 or 200 revolutions to mix. So if I'm optimizing, I want to figure out where the lowest n theta values are. Okay, any questions on that? Let's go back. Now, point of the matter, well, maybe we shouldn't go back just yet. Let's go back. Turn on my pointers again. Okay, this is some data from Ramsey. Ramsey was one of my graduate students, an excellent chap. We can take homogenization number from Ramsey and reduce it by as much as 50%. A reduction in 50% in total cycle time for a batch operation with the potential increase in production rate. So suppose we have 1 hour production rate, half an hour is for mixing. We can reduce it down to 15 minutes instead of a half an hour being 30 minutes. Now production time is 45 minutes instead of an hour. We're running 100 batches, or we could increase things. We can increase the batch numbers we run by 33%. Instead of 1,000 batches, we can accomplish the 1,300 batches. So we have a 30% increase in production. This is not going from poor mixing to good mixing. This is going from good mixing to better mixing. All right. The idea is here we may be, but if we dropped it down to there, it'd be much better. Okay. Wall clearance here, you have the wall, you have the wall, and the ribbon comes up against the wall, and the clearance is the distance between the wall and the ribbon, which is a substantially high shear zone. And the impeller, there's two shear zones around here. One is in here, a very high shear zone, and another one is out here. Small changes at n theta value, I shouldn't say small changes. Changes in the n theta value could have a significant impact on your processing. I don't know if this is a particularly interesting comment, but we'll just go ahead and make it. Down here we have an agitated tank. Up here we have an inline mixer. This is same physics, different equipment. And basically mass transfer coefficient versus power per volume. Agitated tanks are down here, inline mixers are up here, and they sort of fall along the same type of correlation. Useful if you're translating from, say, an agitated tank to an inline mixer. It could be quite useful to you. What's important is the magnitude over here. And here we have an example of static mixer and agitated tank work. Major objective in scale up is the production of surface area, basically production of surface area. So I want you to do a little mixing experiment for me. I want you to add water to honey or corn syrup and mix. How long does it take to mix? And note that it's very important, that miscible phases do not mix instantaneously. Miscible phases do not mix instantaneously. People think they do. Proper perspective. It's important to gain a proper perspective on your process. Proper perspective can solve processing problems. You need to play what I call process Sherlock Holmes in your after product identification. Again, this is a comment being made to me by Don Kessler. For example, let's just take a look here. Filtration unit is stopped. The conclusion, filtration unit stopped. The conclusion is something's wrong with the filtration unit. That's not true. Nothing is wrong with the filtration unit, but it has stopped. Well, the other viewpoint is the filtration unit is doing exactly what it's supposed to do, okay? The problem has occurred upstream. The filtration problem has just received, filtration unit has just received the problem. So where is the problem being made? We got to play detective. So we go after the unusual suspects. Are there too many fines in the filter aid? It's pretty funny. You buy a bag of filter aid. I may have mentioned this earlier, but you buy a bag of filter aid. Right there, it says on there filter aid. When you go ahead and use it, it becomes a filter hindrance because the particle size changed on you. Centrifugal pump was used to feed the filtrate to the filter press. Now, let's call it a centrifugal pump, but indeed, it's actually a hammer mill. A hammer mill being a device that breaks up particles. Maybe upstream you have a slime. Okay, a slime produced upstream. So, playing process Sherlock Holmes is you got to play detective, figure out what's going on. This isn't done by some computer program. It isn't done by software. It isn't done anyway. It may be done by process data. So you want to go out and look at your data. Scale up of a polymer. Okay, that's pretty funny. Very broad molecular weight distribution. This was not observed in the laboratory reactor. Well, the unusual suspect here is the reactor geometry. The reaction takes place below Reynolds number 500. Aha! So here's what we have. What you have in small scale, it's well mixed. Mixing in the laboratory is very common occurrence. No problem. Piece of cake. However, when you scale this thing up, you have a much larger tank. And you do a dummy design, agitator, turbulent agitator, and a laminar application. Remember, we're at 500 Reynolds number. That's a laminar flow. So what happens is you have a well-mixed region, which is right here, which gives you one molecular weight. This is a reactor in here. Okay. And then you have another region out here, which is poorly mixed, which is another reactor, which gives you another molecular weight distribution. So inside your reactor, you have two reactors. You get a twofer. 2 for 1. Well-mixed small tank, poorly mixed large tank. So large scale is far less mixed than the small scale. They have two different reactors in the same geometry, or the same vessel. Occurs in the drug industry and occurs in polymer processing. You have what might be referred to as impeller processes down in here, and then you have tank processes up in here. You have a fight or a duel between impeller-based processes versus the bulk of the tank type processes. Mixing tests. Oh boy. Well, change the impeller rotational speed standard. You can change mixing locations, or feed locations. You can also change feed rate, because whenever you're feeding something, you have jet mixing. And the jet mixing may actually become very important. And of course, you have your old buddy, power distribution in the tank. I already said, if you take a look at the helical ribbon, I already said this, you had the wall and the blade. This is a high shear zone sitting here. And on the inside of the blade as well. The rest of the tank is, do I dare say, stagnant? Well, the rest of the tank may be moving at a lower, much lower processing conditions. Nature of a process mixing problem. Lack of information about the process. You don't know what the N theta values are. By the way, N theta values are easy to come by. You have a tank. You got all that process control data, right? So you have a tank filled with water, and you add salt solution, or you add a high temperature liquid, or you have pH, acid. Anyway, you record the process reaction curve. So it might look like that. So mixing time might be right in here. This is result, maybe the results of your measurements, and this may be time down here. Anyway, right there's your mixing time. Then you pick out the N theta, that's theta. Then you multiply by N, and that will be your number of revolutions to mix. So you go in and you calibrate all your tanks and figure out what the N theta values are. You will also know that the N theta values are primarily a function of batch volume. N theta values will change as I change the tank volume on you. The N theta values will increase. Suggestions may help you. You should define what you're looking for. If you don't know why your process is behaving or acting the way it is, you should find out. Process behavior happens for a reason. Determine the physics of your process. Fluids obey the laws of physics and chemistry. Fundamentals are important and should be the basis of your analysis. You should know the basis of your the basis of why your mixing equipment is working. All right. Find out the different attributes of your process. Calculate the different Reynolds numbers. Look for key problem areas. The key problem areas: insignificant flow velocities, inappropriate contacting, inappropriate phase regimes. You should measure and calculate power input. You should use power meters, rotation counters, variable speed drives. When possible, power meters run on empty, run on full. Take the difference for a crude estimate to the power to the process. Power signatures are important in understanding your process. Let's back off on this and we'll get to show you what I'm talking about. Go up here. Guess we go here. And this is a wonderful flow regime movie that what I'm talking about by power signature. This must be some sort of polymer people are processing. But here we have essentially, we'll pause this. We have essentially goo in here. Pause it. We have goo in here. You can see it. I guess I'm not pausing it. Okay. That's one flow regime. So there's one set of power. There's a set of power. And you can see the goo thickening some more, right? Okay, then we go to this flow regime. Now here is an interesting flow regime in the fact that gravity is no longer working. It's pretty funny that you think of gravity and you don't realize that perhaps in your processing equipment it no longer is working. Nobody's ever told you that. Gravity doesn't work. Anyway, here is an example of gravity not working. That material is clinging to the wall. It is not falling off the wall. It is viscously adhering to the wall. So we have the one regime where it's down in here. We have this regime which is sticking to the wall and gravity's not working. We have this regime where you're starting to form pellets. Okay, so the pellets are starting to form down in here. The regime, the low gravity regime or the viscous regime, whatever you would want to call it, is now being disrupted somewhat. So let's go over here. Now we have a further change, and eventually we start to form pellets. You can see the pellets being formed in here. Okay. And over here we have, what do we have over here? More pellets. And more pellets yet. Now we have it emptying. Talk a little bit about here. Here's a breaker bar back in here. We have a rotating impeller. We have a big clunker there. Now that will stay there forever and ever and ever and not be mixed in. But we have different flow regimes. We have different torque or power draw on the motor. We can use that to advantage. We can use that to advantage. That's what I mean when I say power signatures are important to process understanding. Okay, maybe we should go to the big slide here. Go back to my pointer options. Go for blue this time. I want a pointer highlighter. I want a highlighter with color orange. Hopefully I'll get what I want. Power signatures. So you have time versus down here. This is time. Time down here. T-I-M-E. Anyway, we have power varying up and down like this, and that's your power signature. And you can tell where you are in your process by noting the power. Now, what flow regimes are actually occurring? You want to run tests, make observations. You want to perform mixing tests. Anticipate heterogeneity in all measurements. Perform process studies when opportunities present themselves. Very important. Let's take a look. I've mentioned this earlier, heterogeneity. I measure gas content here, it's 50% gas. Measure gas content up here, it's 15% gas. I measure gas content down here, it's 0% gas. So I have three process measurements. All three of them differ from each other, 0, 15 to 50. They're all accurate measurements, right? So you should be aware of process measurements. Down here we have a slurry pipeline. All the settled solids are at the bottom. We have a high concentration of solids. And up here we have a clear layer. Whenever you're dealing with solids, you should always watch out for clean liquid layer, or what I would call a clear layer, C-L-E-A-R. We'll show you clear layers again later. Okay, clear. No solid. This is clean of solids up here. Clean or clear layer. You should perform experiments and scaling studies whenever as they would occur in the plant. You want to perform research similar to plant equipment. You should choose vendors who will work with you and help you understand your process. Avoid vendors which will solve all your problems, place themselves between you and your process. And you want to make effective use of analogies. This is very important, actually, use of analogies. You want to avoid process myths, dogma, unsubstantiated information. You want to get a second and third opinion. You want to prevent the problem before it happens. You want to beef up the process. You want to do the right type of studies. Cost of pilot plants relatively low. Cost of mistakes in a commercial plant can be very high. Find out why processes fail. Recognize what the problem is. You want to factor, geometry's factor, key factor in correcting mistakes. Play what happens games. What happens if I lost agitation? Is the solids all going to settle the tank bottom? You should avoid problem processes. Should avoid problem processes. Choose the easiest route. You really want to have the KISS principle. You want to break it up into simple steps. You want to avoid a multi-phase processing altogether. That's probably unrealistic since multi-phase may actually be your product. You want to avoid sticky solids. This is tough life here. You want to do the simple things. Pre-mixed tank. It's far easier to mix two liquids together than mix a solid in a liquid, especially on the large scale. You mix the solid in a small amount of liquid, then you take that and mix it to a third liquid. That's probably somewhat advantageous. That's to your advantage. Use pre-mixed tanks for difficult to wet powders. Pre-weigh tanks, mix while filling, vertical plants. In other words, I have a level here and I have another level here. This distance may be 8 feet between floor 1 and floor 2. However, this distance to another plant is maybe 20 feet. Here it's 8 feet. So it's also easier to clean vertically downward. It's also easier to feed vertically downward. So you want to build vertical plants if you can. You want to mix while filling if you can. You want to prevent stratification. See, you have perhaps 16 additions, right? So you have this tank up here. It has this addition, it has this addition, it has this addition, it has this addition, it has this addition. They're all stratified in there. And that's not good, because now you've created yourself a mixing problem. You want to mix while filling. You want to avoid quality problems in your feed. You always want to check feed composition. Obviously, we've already talked about filtration. You want to clean your filters offline. Impeller on the tank bottom, good idea. All right. Simple go and no-go tests. You have something called capillary suction test for filtration. You can have a plugging test for Bingham plastic, or you can have a test side by side for bubbles and drops, test for coalescence. Those are some simple tests. If you contact me, I'll give you the information about them. But the idea of pilot plant studies, you should develop these as you go through. Okay. Analyze power input throughout the cycle. Don't parallel feed in a static pipeline or a pipeline. Don't recycle. Does your process perform well without recycle? Feed at a right angle with sufficient momentum for the stream to reach the far end, far wall. Let me talk about some of those. Let's talk about capillary suction test. You get a test tube, invert it on blotting paper. So you have your filtrate in here. And basically you'll build up a filtrate cake right in there. And you'll have timelines in here as the filtrate goes through the cake and into the blotting paper. This essentially gives you a measure of cake resistance. Capillaries, that would be called the capillary suction test for filtration. You also potentially have a plug system. You have a system that's filled here. This is to determine the yield point. All right, you plug a tube with material. You put higher pressure on here, low pressure here, and you know the length of that, and so you do a simple force balance, 2 pi r L, 2 pi r L. The yield point, which we'll write as tau, this is a tau, equals the pressure drop times the area. And this is the yield point. This is what you're after right here. And that would be an example of a plug tube test for a yield point. What was the other test we were talking about? Also bubble test or coalescence test. You could come in with a capillary tube with two bubbles generated at the end, right? And you see if they coalesce here. Surfaces carry charge, and this will give, it's a crude test, right? A crude test. And it can tell you the effect of surface charges. The videotape on surface tension, which I haven't talked about, has two parallel plates of glass, right? And basically they have a liquid in between the two plates. And what you have is a foam meter of sorts. And maybe we'll get to that a little later. Foam meter of sorts. So what may not be significant, anyway, I was reading here, this may not be significant effect for some effects, maybe profound for others. Capillary suction test, Bingham plastic for test of Bingham plastic for yield point, side-by-side bubble comparisons, and now we have this simple foam meter, which we can talk about a little bit later. The idea of feeding at a right angle, right? You have a pipeline, right? It has a side feed coming in. So you have A sitting here, and B's coming in down here. B's down here. So you want to hit the far wall so it spreads out and reaches the shear layers. And this will be a good mixer. That's why you want to feed at right angles with sufficient momentum that this stream will hit the far wall and spread out. Some tricks of the trade, so to speak. Anyway, so you have a house divided. You have the chemists over here and the engineers over here. I've run into companies like this. We won't name them. Basically, you have one kingdom and another kingdom and a, how can I say it, driveway down the middle, or driveway. No. This is a no man's land or no woman's land these days. And you have a throw it over the wall mentality. What you want to do is make sure everybody's talking with everybody else. Even this is bad, because the chemists over here and chemical engineers here, you need to mix them up. The plant should be in the lab, and the lab should be in the plant, so you get all kinds of good cross-talking. This is why you want your employees to go to lunch together. You want the chemists and chemical engineers, the biologists and the mechanical engineers sitting there, the maintenance crew and the maintenance and operators, they're all sitting there talking with each other. And they're talking about all kinds of things, but central to their life is the job, and so they'll probably be talking about the job for half the time. People need to interact on a daily basis. Problems are never completely solved. Solutions are forgotten. The plant historian is very important. Flow visualizations help in understanding. Don't invent the wheel. I was at a very famous paint company up in Minneapolis, Minnesota, and these chaps they're a very nice group of people, don't get me wrong. But they're typical. They were each in their individual plants and working on the same problem. And one had one solution and the other had another solution. If they had worked together, they could have probably have solved the problem much more effectively. Wait a minute, I don't think it was a paint company. I think it was a food company. Yeah, a food company had that problem. I see a lot of companies have a lot of issues. Communications is probably one of the more significant problems that companies have. People don't talk to each other. It's a shame. Anyway, better to make improvements on the wheel already, and hindsight is the best design procedure. And again, I would I don't have my list of literature here. Usually I give you a fairly extensive list of literature. Sorry, I don't have it here. And what I would recommend is the technical literature is highly significant. My friend Dick Goodley basically went through a pile of all kinds of stuff per month, looking at advertisements, reading technical articles, seeing if there's anything of any interest in his for his work. And that's the idea of keeping current on what is out there. I was visiting one company one time. I was going through a meet and greet type of situation where I sat down with a number of employees for the day, and this one chap told me what he was going to do for the next 6 months. I pulled out the paper that already had his results there. So he didn't have to do that. Or if he did it, he had backup confirmation about what his results were going to be. The technical literature is extremely effective. And with that, I'm going to stop right here and tab G, and we'll pick this up later, I think. And you all have a good day, or the rest of your day. And again, if you have any comments, questions about this, you can certainly contact me. Let's see if we can get out of here. Let's go up here, end the show, discard, go to the top. And my email is the best way of contacting me. And my telephone number may or may not change. And of course, my books are available. They're cheap. They're meant to be cheap, so everybody would buy them. Your company can buy them for you. And we'll pick up power next time. And let's see, where are we in the listing of fluid motions there? And this is power sitting here. So we're about halfway through the course, where this is tab 263, and we'll pick it up there next time. Thank you, and you all have a good time. And again, you have my contact, and you have a good day.